Hello and welcome back to Basic Topology, the video series where we talk about topologies, Hausdorff spaces and related stuff. And indeed, in today's part 7, we will show that in Hausdorff spaces, compact sets are always closed sets. Maybe that does not surprise you for ordinary compact sets in Rn, but in general topology, this is something we need to prove. But as always, before we do that, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And as a reminder, you can click the link in the description to download additional material for the videos. And with that out of the way, we can immediately start recalling the definition of a Hausdorff space. It's actually not complicated at all, because it's just a topological space with one additional property. And in short, we can say it's always possible to separate two different points. And more precisely, this means that for two different points x and y from the set X, we can find two open sets, which we call ux and uy. And as always, open just means these are sets from the topology T. And now the open set ux should be a neighborhood of x and uy an open neighborhood of y. And we already know for an open set this is quite simple, it just means that the point itself lies in the set. And now finally, separating the points means that we can choose these two neighborhoods such that they are disjoint. Hence the intersection here should be just given by the empty set. Okay, so this was nothing new, this was just the definition of a Hausdorff space. And here the topic of this video is a nice thing we can do in a Hausdorff space. Namely, we will look at a compact set in a Hausdorff space. And perhaps a good name for the compact set is a capital K. And at this point you should know that compact means that any open cover for K has a finite subcover. And now we can show by having this property, K has to be a closed set as well. So maybe this result is not so surprising for you if you already know some analysis, but the crucial thing here is that this holds in any Hausdorff space, which means we simply don't need any more structure than that. Okay, so now for the proof here, the picture might be quite clear. We have our topological space X, and then inside we have a subset K, which should be compact. And here you see everything outside of the set K is the complement of K, and we want to show that this complement is an open set. So please recall, this is exactly the definition of a closed set in a topological space. And in order to do that, the first step here should be to use the Hausdorff property from before. This explicitly means that we can separate a point P outside from a point Q inside. Hence, for the 2 points Q and P, we find two open neighborhoods that are disjoint. And now the thing is that we definitely need good names for them, so let's use the capital letters U and V. So in the picture here on the left we have an open set U and on the right an open set V. And now in the index I want to put P and Q because the choice of the two open neighborhoods definitely depend on the chosen points. And here please note that P and Q are always two different points because the one point lies in K and the other one in the complement. Hence, as stated before, we can always choose them in such a way that they are disjoint. And now since this works in general, we can fix the point P and vary the point Q in K. Therefore we can form the union of the neighborhoods where Q goes through K. And since each Q lies in UPQ, we have an open covering of the set K. And there you see, this is where the compactness of K can come in. This means we don't need to use all the points Q in K, it's sufficient to use a finite subset. So this is our finite subcover, and let's say we go through the numbers 1, 2 until n. So this includes that we choose some special points Qi. We don't need to say more about the choice of the points, because we know by compactness that such a finite list exists. Moreover, corresponding to these sets U, we also have the sets V. And please don't forget, these are still open sets and each V is disjoint to the corresponding U. Therefore, we can just look at the intersection of all the V sets. And this is a finite intersection, so the result is still an open set. And it can definitely not be the empty set because all of them contain our point P. So indeed the intersection here could be quite small, but it's still a neighborhood for the point P. So if we want, we can give this intersection a new name. Let's call it BP. And here you should note, because BP is the intersection of all the sets, BP is disjoint to all the U sets in the union here. In other words, it cannot have any overlap with the whole union. Which also implies that the intersection with K is empty as well. And obviously this holds no matter which point P we chose at the beginning. And this is really helpful because we can also form the union over all these sets BP. So we just go through all possible points P from the complement of K. And since P definitely lies in BP, we cover the whole case C with this union. And at that point you should recognize that we can simply put both pieces of information together. If the union here covers the whole complement of K, but we don't have any intersection with K itself, then we need to have an equality here. Hence, the complement of K is a union of open sets. And we know by the definition of a topology that a union of open sets is still an open set. And this is exactly what we wanted to show. The complement of K is an open set, so K itself has to be a closed set. And this finishes our proof. A compact set has to be closed in a Hausdorff space. This is a nice result, which we will definitely use in later videos. However, first I want to talk about some more special properties a topological space can have. This is something for the next videos, and I really hope I meet you there again. Have a nice day and bye bye.